Okay, in our last video, we went through 4 examples doing implicit differentiation. Let's go ahead and do a little bit more advanced practice with this implicit differentiation. So let's say I want to determine an equation of the line tangent to the graph at the point 1, -3. So I know if I need a tangent line, I'm going to need a point, and that's already provided to me, 1, -3. But I'm also going to need a slope, and that slope is going to come from my derivative, dy dx, at that point 1, -3. So I need to differentiate here. The derivative of x squared is 2x minus 3 times the derivative of xy, a product rule. So x times the derivative of y plus y times the derivative of x equaling 0. Okay, and I have this at the point 1, -3, right? Some people like to solve for y prime first, so I'll use that approach here as well. So 2x minus 3x y prime minus 3y is equal to 0. So that would mean that negative 3x y prime is going to be equal to 3y minus 2x. All right, divide everything by -3. That means that y prime is going to be given by 3y minus 2x, all divided by -3x. Now, I know my point 1, -3, so that means that y prime is going to be 3 times -3 minus 2 times 1 all over -3 times 1, substituting the x and the y value. If I do that, that gives me in the numerator -9 minus 2, in the denominator -3. Simplifying that gives me 11/3. So therefore, using the point slope form of a line, y minus y1 equals m times x minus x1, right? My tangent line is going to be given by y minus the y value being equal to the slope times x minus the x value. Okay, and if your professor wants you to say y plus 3, that's fine. If you would prefer to have the minus 3 on the right side of the equation, you may. But here is an equation. It happens to be a point slope form, but we have an equation of the line tangent to our graph at that point 1, -3. Okay, let's look at another example. Look at this. We have differentiation, but now we have this with u's, right? And I have here we're being asked what is dy du. We have y is equal to x squared minus 2x, u is equal to 2x plus 1. So what is dy du? Well, dy over du I can think of as dy over dx times dx over du, right? I can use that Leibniz notation as one approach for finding my work, right? So we can say, okay, well, if that's going to be the case, right, dy dx for this first one, dy over dx is going to be equal to derivative of x squared, derivative of 2, okay? And for du dx, well, du dx, the derivative of u with respect to x, well, that's just going to be 2, right? But I want dy dx times dx du, right? So that means that the reciprocal of du dx, in other words, dx du, is 1/2. So therefore, dy over du, which is equal to dy over dx times dx over du, is going to be 2x minus 2 times 1/2. And that means then that dy over du is going to be equal to x minus 1. Okay. Now, technically, there is another approach that we could use to solve this. We could say, hey, let me take the derivative with respect to u of both sides of this equation. Right? So for what I have on the left side, derivative with respect to u, I would have dy over du is going to be equal to 2x times the derivative of x with respect to u minus 2 times the derivative of x with respect to u. Right? And we also have that 1 is going to be equal to 2 times the derivative of x with respect to u. So therefore, the derivative of x with respect to u is going to be 1/2. And that would mean that dy over du is going to be 2x times 1/2 minus 2 times 1/2, which is x minus 1. Right? So it doesn't matter which approach we use. If we want to use this Leibniz approach, or we want to use more related rates approach, but we have this idea of the finding a derivative with respect to another variable that is present within implicit differentiation, but also present within related rates. Right? And you can see kind of an aspect of both within this example. Okay, so let's look at another. Okay, our last example looks like for this one. So here we have x plus 2y times dy dx is 2x minus y. And we want to find the value of my second derivative. All right, I want to find the value of the second derivative. Well, to find the value of the second derivative, I need to take a derivative with respect to x of both sides of my equation, because this is saying take a derivative twice where the variable we're considering is x. So for the first one, we're going to have, I'm going to rewrite this to make it easier for me to consider in my brain. I'm going to say x plus 2y times y prime equals 2x minus y. Okay, so if I'm going to differentiate the left side, I have the product rule. X plus 2y times the derivative of y prime, which will be the second derivative, plus y prime times the derivative of x plus 2y, which would be 1 plus 2y prime. And then that's going to equal the derivative of the right side, which would be 2 minus y prime. So ultimately, we're trying to solve for what is this value of y double prime. But we know that we're going to work with it at the point 3, 0. So what does that mean for us? Well, I know that 3 plus 0 times y prime needs to equal 2 times 3 minus 0. Okay, so that means that y prime at the point I care about is going to be 6 divided by 3, which is going to be 2. So now I can come and substitute. X plus 2y, we said, is 3 plus 0. I'll just go ahead and write 3 plus 0. Y double prime, we don't know, we want it. Plus y prime, we just said y prime was 2. And then 1 plus 2y prime, well, 2 times 2 is 4. And that's going to be equal to 2 minus y prime, and we said y prime was 2. So 3y double prime plus 2 times 5, that's 10, has to be equal to 0. So that means then that y double prime at the point 3, 0 is negative 10 thirds. Okay. Now, where could we take this problem a little bit further? Well, for us, we could say that, hey, my first derivative is positive, right? The first derivative that I have is positive because it's 2, and the second derivative is negative, so that means that my graph has to have some sort of positive concavity, or excuse me, positive slope with negative concavity for my particular spot at the point 3, 0. I also know that the point 30 is going to be a point that is on the x-axis. Right? And I also know that if I was going to make a tangent line there, that tangent line would lie above my curve and would overestimate the actual value of my function. If I was going to use the tangent line to approximate, let's say, my function value at 3.1. So lots of places that we could go with this, understanding concavity and slopes and tangent lines. But that's a quick piece with differentiation, in particular implicit differentiation, with a little bit looking at second derivatives. Okay. Thank you very much for your time. Have a wonderful day.